Welcome, ladies and gentlemen. May I have your attention, please? Please raise your hand if you did not graduate today, the 4th of April. Okay, let's go ahead and begin our discussion. With particle motion, right, you already have a good understanding of the connection between distance traveled versus velocity versus acceleration from your experience first semester and in physics or other classes. We want to make sure that we're making the calculus connection. So how is it that we can answer calculus questions involving displacement or distance traveled, right, using techniques that we developed throughout the year? We've got our differential calculus where we use derivatives. We've got our integral calculus where we use integration. And so for this first one, let's see what we're going to use. For what values of t is the particle moving to the right, moving to the left, or at rest if we're given a velocity function v? Well, recall that velocity is directed motion, right? The sign of velocity tells me the direction that the particle is moving. And so for positive velocity values, we know the particle is moving to the right. For negative velocity values, my particle is moving to the left. And if the particle is at rest, that's just code for stopped, where its velocity equals 0. So to answer this question, it looks like we don't have to differentiate or integrate. In fact, we can take our velocity function as is and set it equal to 0. So we'll go ahead and take my velocity function v of t, and at rest means the velocity is 0, right? And so this is basically like finding my critical values for position. And then we'll go ahead and do a sign test on a velocity number line. And so wherever velocity is positive, then we've got particle moving to the right, and vice versa for negative. All right, so here we go. What technique might we use to solve a quadratic equation in standard form set equal to 0? Factor first or fail. And so we'll go ahead and set up my parentheses. There we go. Looks like it's a t squared, so t and t. And go ahead and show your combination of factors such that the outer product and the inner product sum to give us that middle term. So what do you get for your factorization here?
T minus 5 and t minus 2.
T minus 5 and t minus 2. Right here, and we have the same factorization as Joel. Nice job. Set each individual factor equal to 0 and solve separately. So it looks like the particle is at rest at t equals 5 and t equals 2. Awesome. Let's go ahead and make a velocity number line. We'll label it as such, just like we labeled our y prime or y double prime number lines in the past. So we'll go ahead and make our v of t number line. Just like critical values from Unit 8 when we're talking about function behavior, the only place the particle can switch direction is at the critical values, where velocity equals 0 or is undefined. And so these are the only places that it could change direction. So it looks like 2 and 5. Go ahead and share with the class a convenient time t value to the left of 2 that I can use in my sign test. Hayden?
1.
1, I'm down, so I'll go ahead and plug 1 in. Then I get negative times negative. Overall is positive. A convenient value on the next subinterval, Tyler?
3.
3. Negative, positive, overall, negative. And a convenient t value on the next interval, Michael?
6.
6. I'm down. Positive, positive, positive. Great. So we can see from our sign test and analysis that the particle is moving to the right on the time interval t equals 0 to 2 and 5 to infinity. The particle is moving to the left on 2 to 5. So all we need to do now is state that. If we needed to include a reason, because this is a free response portion, and it said justify your answer, we would say because velocity is positive. Particle moving to the left on 2 to 5 because velocity v of t is negative. Raise your hand if you already found that. So who found that on your own? Non-calculator? No biggie? Great. So then what if we're going to find the displacement of this particle over the time interval 1 to 7? So if this is calculator allowed, we know that we can find the displacement simply by setting up a definite integral in between my left bound and right bound of my time interval, 1 to 7. And so I know that the displacement, right, the displacement, that is the change in position over a closed interval for a particle, is simply the integral of velocity from A to B. So for us, I know the displacement, I'll abbreviate displacement, is given by the integral from A to B, my closed interval of my velocity function as is with respect to time. In the context of this problem, that is the integral from 1 to 7 of my velocity function. Since it's defined, you could just put v of t if this were calculator allowed. I'm going to go ahead and write it though. T squared minus 7t plus 10. And if this is calculator allowed, right? This is calculator allowed. After showing the calculus and writing that down, I can simply go and math 9 it. So that's a big time saver. I can go to my calculator and we'll just math 9, my favorite calculator function. Looks like from 1 to 7 of my velocity function was t squared minus 7t plus 10. Close it with respect to x, and voila! It looks like 6 units is the displacement of the particle over the time interval 1 to 7. Raise your hand if you already had 6 units. So 6 units? Yes! You guys are killing it. Good job. Contrast that with distance traveled. So how is distance traveled going to be different than displacement? Well, distance traveled takes into account that sometimes when a particle is moving to the right, sometimes it's moving to the left, but all the time that distance traveled is going to be counted as a positive, right? We're going to count that change and get the total distance traveled over the time interval. So if this is calculator allowed, this is a super easy question too. We'll simply integrate the absolute value of velocity so that any negative portion of the graph is flipped over the x-axis, any positive portion of the graph remains above the x-axis, and I count all of that as a positive contribution. That's it. So I'll go ahead and abbreviate now distance traveled. I know that that's the, in general, integral from a to b of absolute value of v of t with respect to time. In a specific context, that's integral from 1 to 7 of absolute value of t squared minus 17 plus 10 closed bars dt. We saw in our activity from last time, if this were non-calculator, I'd have to go ahead and determine the zeros of that quantity inside, use my sign test, and take the opposite of the velocity over those negative velocity intervals, and break it up into 3 separate intervals, right? But because this is calculator allowed for number 3, I'll math 9 it again and simply include my absolute value. So what's that? That's math 9 and 1 to 7 again. But this time I'm going to go math num abs for absolute value. So math, right arrow over to the number one, and then absolute value. And the same function, t squared. Did I get it all? 7x1, and think we're good? We'll give it a shot. Ooh, it's thinking. Still thinking. 15 point, gosh, it's given the old college try, isn't it? So when we see this on our graphing calculator, we're thinking, okay, so did it really go 15.000000559 units? No, the calculator is using approximations to do this, right? It's doing the best it can. You should recognize that 3 9s in a row or 3 zeros in a row type thing is probably trying to give you the exact answer, right? A whole number, in this case 15. So I would not put 15.000. I would put 15 here. 15 units. Raise your hand if you already had that. So you already found 15. Hey, great. So calculator allowed, displacement versus distance traveled is super easy. How would we have done number 3 if we were not allowed the use of the calculator? Right? If we were not allowed the use of the calculator. Well, if we were not allowed the use of the calculator, Now we've got to consider when my velocity function was positive versus when it was negative. And so if we look at our number line, whenever velocity is positive, right, it's going to be counting distance traveled as a positive contribution. But on this middle interval, from t equals 2 to t equals 5, this negative, right, this negative velocity is going to be subtracting off of your position. We want to count that as a positive contribution to overall distance traveled. So what am I going to do? I'm going to take the opposite of the velocity function on this negative interval, that is, flipping the velocity function graph over the x-axis so that it counts as a positive contribution along with the other two subintervals. So let's go ahead and break up my original absolute value. So we'll break up my original absolute value. Integral from 1 to 7 of absolute value of t squared minus 7t plus 10 closed bars dt. That's equivalent to the integral from 1 to 2 of regular velocity with respect to time, and then plus the integral from 2 to 5 of the opposite of my velocity function. Uh-oh. Plus the last remaining portion of velocity was positive, so that's 5 to 7 of t squared minus 7t plus 10. And we would do each of those separately. Non-calculator, well, in accordance with the fundamental theorem of calculus, part 1, find an antiderivative function, right? Evaluate upper, evaluate lower, subtract. Then you get your answer for each of the separate ones, and then add them together at the end. Sophia?
So the integral from 2 to 5.
Yep.
Can you put the opposite sign where you put the plus sign, or does it have to be?
Yes, absolutely. We know this is just a constant multiplier, so we can pull it out in front and just have a minus, right? Minus there and fine, or we can distribute it through and have my integrand function be negative t squared plus 7t minus 10, right? It's all your choice. In fact, right, this doesn't look very good. We want to make sure we're not thinking of this as subtraction. This is the opposite of this, right? Opposite of this. So I was just writing the original to drive home the fact that we're taking the opposite of velocity on any time interval where velocity function is negative. You guys good? And there's an easier way, I think. Instead of breaking this up into 3 separate, right, integrals and doing each one by hand, finding an antiderivative function, evaluating by hand, it might be easier to make a position chart, right? We know the only place that my particle can change direction is at my critical value, when my velocity equals 0 or is undefined. And we already saw that that happened at t equals 2 and t equals 5. Those are the only places where my particle can change direction. So if I simply create a position t-chart, a time, a t(x) of t chart, kind of like the closed interval method, and throw in my endpoints 1 and 7, and any critical values in between, which included 2 and 5, I could evaluate the position, right, at each of those places, and then just take the change in position, right, when I was moving to the right, moving to the left, moving to the right, count them all as positive contributors, add them together, and get the 15. And so, in order to do that, though, I need position. Was I given position? No. Crikey, I was given velocity via t. If I'm given velocity, then how would I get to position, right? How would I get to position if I'm given velocity? Riley?
Antiderivative.
Yeah, I could take the antiderivative, right? I could take the antiderivative. Now, I don't have an initial condition. So anytime I integrate, right, a function and find it's the antiderivative function, I need to include that constant integration. But it's not going to matter when I'm talking about the distance traveled over the interval. It doesn't matter if we start at a base camp of altitude 8,000 meters and go up 200, down 100, and up 300. It would still be the same distance traveled, right? If I had started at a base camp of sea level and gone up the same amount, down the same amount, and up the same amount. And so I'll include that plus c there, but it's not going to matter in my overall calculation. So once again, t cubed over 3 minus 7t squared over 2 plus 10t plus c. Evaluate it at each of those, and then take the net change in position in each of these, such that these are all positive contribution. Add them together, and voila, we'll get our final answer for distance traveled in OE 15 too. In the interest of time, we're not going to do those methods. We know how to find an antiderivative and evaluate it, and so we're not going to go ahead and do those right now because I want to make sure we have time to develop our average value formula. But first, we'll go ahead and pause the recording and take care of our OTL number 1 check. Okay, ladies and gentlemen, so our tests will get back next class so we can see exactly how we gain and lost partial credit, and I hope to have them in for B day, even though your class is on A day, so that you can at least see, because I know, right, I know that you're biting your nails and biding your time, and so hopefully I can get those in as soon as I finish. So I want you to think about how you calculate an arithmetic mean, that is, an average, when you're talking about a finite number of entries, like our unit test scores, for example. I mean, how would you find your average test score for the semester? Well, what would you do if you've taken, let's say, 5 unit tests during first semester? What is it that you do to find the average of those? Riley E? Absolutely. We add them all up and divide by the number of entries. And so we can take our score 1 plus score 2 plus score 3, and so on and so forth, and divide by the number of entries that there are. In this case, there's 3 entries. Finding an average value of a finite number of entries is easy cheesy. But what if we extend that to the continuous, right? To the continuous sense, not the discrete sense. That is to say, what if we're talking about a function over some interval a to b that has not 1 value, not 2 value, not 3 test scores, but an infinite number of function values, right? An infinite number of function values attained in between a and b, such as the case of a continuous function. So we're talking about, what if we had some function that looked like this, right? And we're thinking about what's the average value of this function f on the interval a to b. Well, I don't know, but visually we could know some things, right? We would know that it would have to be, well, in between this maximum value and in between this minimum value, and we could visually estimate, I don't know, if we could only add up all of those function values, right? If we could add up all those function values and divide by how many there are, well, that's not possible in this case because there's an infinite number. And yet, we'll still be able to calculate average value, right, using calculus. Because if there's one thing we've learned from calculus, it's been a recurring theme, it's our ability to handle an infinite number of, well, in this case, function values, just like we handled an infinite number of rectangles, right? Limits was our tool to get at that continuous infinite sense. And so we're going to do the same thing in today's class period. We'll develop and apply a formula for the average value of a function f over an interval, and we'll apply that to continuous functions. So I'm pretty excited about that, as you can see. Let's add our stamp eligible items to our agenda. We've got 5, 7C, 10, and 13. So 5, 7C, 10, and 13. And then I do have a separate handout for you that includes our mean value theorem formula, but I didn't want to give it to you first. I wanted you guys to develop it in the activity, and then when you come back together for our discussion and closure, I'm going to give you guys a handout. We're going to make a graphical connection between average value, the mean value theorem for differentials, and the mean value theorem for integrals. So today's a big day where we connect first semester material with second semester material. All right, I'm going to go ahead and stop the recording. First. Okay, ladies and gentlemen, so as a result of our activity, we now have a formula that will allow us to calculate the average value of a given function, even though it's continuous over some interval a to b. Even though that function contains an infinite number of values, right, over the course of the interval a to b, we can still calculate its average value exactly and algebraically, as the case may be if we're given a function definition symbolically. So if f is continuous on an interval a to b, and then there must be some x value, x equals c, on my interval a to b, such that f of c, where we'll call that my average value, or y average, the average value of that function over the course of the interval is gained by summing up all of the function values, right? Where I can still interpret that integral symbol as an elongated S for sum of all of my function values from A to B, my lower limit to my upper limit, and then divided by the length of my interval, right? All the places where I can look and find those x values, that is B minus A. Sometimes you'll see that as particular if you're a multiple choice. This is a constant, right? And so we might see that out front as 1 over B minus A, like 1/16 of the integral from A to B, right, of f of x with respect to x. Some key things to point out before we do an additional expression is that if I'm trying to find the average value of f, I'm integrating f and dividing by the length of the interval. If I want to find the average velocity, I'm integrating the velocity function and dividing by the length of the interval. If I wanted to find the average rate of oil consumption, I'm integrating my rate of oil consumption and dividing by. So these match. If I'm trying to find f of c, I'm integrating f, dividing by the length of the interval. If I want to find g average, I'm integrating g, dividing by the length of the interval. So those things match, okay? Just like your test scores. You're adding up test scores, right? And you're getting an average test score. And so those units and labels and functions have to match. Great. An alternative way to think about this is if we took that b minus a, the length of the interval, right, and interpret that now as geometrically the base of a rectangle, such that when multiplied by the height of my rectangle, y average equals the value of the definite integral, the exact area underneath the curve. What? Well, if we took that y average, right, and we multiply it over by this quantity b minus a, we get the width of my rectangle when multiplied by the height of my rectangle equals the exact area in between my function f and the x-axis over the interval a to b. Here was your irregular shaped region that you shaded, right, that had part of a parabolic curve as its boundary. Irregular shaped region, right, exactly and algebraically we can calculate that. Well, if we had the perfect height of a rectangle, call it y average, and multiplied by the width of the rectangle, we get the exact same area, and that was one of your stamps. The same area is represented. That's pretty sweet. All right, let's go ahead and sum it up with our closure. The mean value theorem for derivatives algebraically says that if I've got a continuous and differentiable function f over the interval a to b, right, then there has to be some x value, call it x equals c, where the instantaneous rate of change of my function g, call it g prime, is equivalent to the average rate of change of my function over the course of the interval a to b. So that would be given by the slope of the secant line, g of b minus g of a all over b minus a. And that was our mean value theorem back at the end of semester 1, beginning of semester 2. That was our mean value theorem for derivatives. Graphically, we could show that with my slope of the tangent and slope of the secant, and parallel lines would mean their slopes are the same, my equal sign. So let's go ahead and do a quick sketch for that. So if you consider some arbitrary function g over an interval a to b, we know that if g is continuous in between, right, and differentiable on the interval a to b, then there's got to be some c value where the slope of the tangent line is equivalent to the slope of the secant line between the endpoints. And so if I could just draw that, and then let me do it. Can I do it? We're going to try. Oh yeah, big time. There's got to be some place, right, where the slope of the tangent line is the same, and we'll call that x equals c. So I'm going to drop this point of change c down right here, and we'll call that x equals c. Happens right about here. Everyone remember, right? Remember our mean value theorem for derivatives? Contrast that with our mean value theorem for integrals, right? Now we know algebraically that for a continuous function on my interval a to b, that there's someplace x equals c where there's a function value. Call it f of c, or y average, that is equal to, right, that's equal to the exact area in between my function f of x and the x-axis on my interval, divided by the length of my interval, b minus a. If I rewrite this by multiplying that over, then we could draw this visually, right? We could draw this visually. Now as some function f on an interval where the exact area underneath the curve in the x-axis on the interval a to b is equal to this f of c value, which is the perfect height of a rectangle, such that when multiplied by the width of the rectangle, b minus a, is equivalent. And so we could have this green area would be equivalent to the red area. How would I know that? Well, visually I could take this top blue part, right, that extends above my rectangle F ab, scoop it off and smoosh it down into that corner, and it would fill it up exactly, right? If I had Play-Doh or that model magic, that stuff is fun, right? We could go ahead and cut that top part off and smoosh it down. Awesome. Okay, ladies and gentlemen, I'm going to go ahead and stop the recording. You guys are great. Next class we'll practice with continuous functions.